When we look at the incredible recent advances in AI and robotics, you often see robots carefully folding laundry, picking up household items, making coffee,
How am I doing so far?
Killing it.
These are what we might call System 2 tasks. They are deliberate, quasi-static, and rational. You can comfortably teleoperate a robot to do these things, record the data, and use behavior cloning to teach a neural network. But what if we want a humanoid robot to play basketball, perform a fadeaway jumper, or sprint across a discontinuous terrain, or throw its entire body weight into opening a heavy door? These require whole-body agility. This is System 1 territory, pure intuition, instinct, and raw cerebellum power. You cannot teleoperate agility. If you could puppet a robot to do a perfect backflip, you have already solved the physics problem. You also cannot just ask Michael Jordan for a spreadsheet of his joint angle trajectories during a slam dunk. To give robots System 1 agility, we cannot rely solely on human demonstration. We must simulate, and then bridge the gap to reality. Let's explore the evolution of how we do this, from Sim-to-Real 1.0 to 4.0. For decades, the control theory community has used what we can call Sim-to-Real 1.0. The idea is simple but beautiful. You take a highly complex robot and abstract it into a simplified mathematical model, like an inverted pendulum. Then, using Model Predictive Control, or MPC, you solve a real-time optimization problem to figure out the best action to take right now, keeping the robot balanced. What is fascinating, and perhaps a bit limiting, is that there is zero learning here. No memory, no pre-training. It relies 100% on lightning-fast online reasoning. Recently, we have pushed this to Sim-to-Real 1.5. Instead of simplified models, we use massive full-order physics simulators and parallel sampling to compute movements.
But doing this pure mathematical reasoning on the fly is computationally heavy, and it requires perfect state estimation, knowing exactly where every joint is in space at all times. Enter Sim-to-Real 2.0, Deep Reinforcement Learning. Instead of calculating the physics in real time, what if we let the robot fail millions of times in a massively parallel simulation and bake all that physical intuition into a neural network? Algorithms like PPO act as incredibly strong optimizers. They take in raw observations, like joint positions, and instantly spit out the best action. We can use this to retarget human motion capture data. We track the human motion in a privileged simulation that knows everything, and then distill that knowledge into a student policy that only relies on the sensors the real robot actually has. This is how we get a single humanoid policy to play tennis, sweep the floor, and recover from being pushed. But there is a catch. The learning only happens offline. Once deployed, the brain is frozen. If you look at the optimization landscape of Sim-to-Real 2.0, you immediately see the problem. Let's plot performance in simulation as an orange curve and performance in the real world as a green curve. Notice two things. First, there is a massive gap. The physics of reality are messy. Motors degrade, friction is unpredictable. Second, reinforcement learning is a lazy, opportunistic optimizer. it will find the highest peak on the simulated orange curve, exploiting tiny loopholes in the physics engine. But when you deploy that perfect simulated policy in the real world, it completely faceplants. It falls right into a valley on the green curve. Historically, researchers solve this via graduate-student descent, manually tweaking rewards for months until it works. We need a better way. This brings us to Sim-to-Real 3.0, which focuses on real-to-sim, bringing the simulation closer to reality. You might think, why not just learn a neural network to model the residual dynamics, the difference between the sim and the real world? Well, humanoids are highly complex, and RL tends to exploit any slight inaccuracies in a learned dynamics model.
Instead of modifying the physics simulator, Guanyashi's lab introduced the ASAP framework, learning a delta action model, or delta A. Here is the intuition. We record a trajectory in the real world. Then, we replay those same actions in the simulator. Because of the reality gap, the simulated robot drifts off course. We train a closed-loop model, delta A, whose sole job is to inject tiny corrective adjustments to the simulated actions until the simulated trajectory perfectly matches reality. If an action plus delta A in simulation looks like the real world, then we can fine-tune our policy in simulation using delta A as a translator and safely deploy the original policy back to reality. It effectively aligns the physics. The second half of Sim-to-Real 3.0 is structured RL. Remember that jagged optimization curve? We can smooth it out by baking human-like structural priors into the neural network architecture. Take heavy-duty loco manipulation, like a 30-kilogram robot pushing an 85-kilogram cart. If you ask a single neural network to handle this, it struggles. But humans do not control their bodies as one monolithic block. Our upper body manages fast, high-precision dynamics, while our lower body manages slow, robust locomotion. Sickly deploying the RL agent into a dual-agent framework, one for the upper body and one for the lower body, we give the optimization a much smoother path. The upper body corrects quickly to keep an end effector stable, say holding a glass of water, while the lower body steps at a slower frequency to maintain balance. So where does this all lead? If we map out this journey, we have a spectrum from simplified mathematical models to full generative physics simulators, and we have an axis of when the robot thinks, purely offline training versus purely online reasoning. Sim-to-Real 1.0 and 1.5 lived in the online reasoning world. Sim-to-Real 2.0 and 3.0 live in the offline training world. Sim-to-Real 4.0 is the synthesis. It is the realization that offline and online learning combined are incredibly powerful. In the future, we will see robots with a deep learning intuition that gives them a brilliant starting guess, a System 1 reflex, which is then instantly refined by a lightweight online optimal control layer, a System 2 check, preventing them from falling. By blending the raw agility of deep RL with the rigorous safety of control theory, we are stepping into an era where robotic movement will soon rival and perhaps surpass human agility.
You know how you can just glance around a room and boom, find your keys? Your eyes just dart around and you lock on. Seems so simple, right? Well, for a robot, that is a huge challenge. Today, we're going to dive into a system that's learning how to look, just like we do. So, say hello to iRobot. Its whole job is to pick up that towel and drop it in the bucket. Simple enough. But here's the kicker. When it starts, it can't see the towel or the bucket. They're totally out of view. It has to physically turn its head, its mechanical eye, and actually search the room to find its targets before it can do a single thing. And that right there is the big question, isn't it? This isn't just about seeing a picture. This is about searching. So how in the world do you teach a machine that intuitive, active process of looking for something that's not even in the picture to begin with? Well, to figure that out, we've got to first look at why the old way just doesn't work. Right, so to really get why this whole searching thing is so tough for a robot, we need to talk about the huge fundamental problem with how we've usually taught AI to see. Okay, so for most AI, vision is totally passive. Here's what I mean. Imagine trying to understand an entire novel by crunching it down into just one sentence. That's kind of what these models do. They take an entire image, the whole thing, and just compress it all down. Now, for a simple little picture, maybe that's okay. But in a big, messy, cluttered room, it's like trying to find one specific word in that one crunched up sentence. It's just completely inefficient. And the classic Where's Waldo puzzle is the perfect example of this failure. You and I, we find Waldo by actively scanning the page, right? We ignore all the silly distractions. But an AI that tries to just swallow the entire image in one gulp, it gets totally overwhelmed by all that visual noise. And, well, it can't find him. Actually, our own brains have this really clever trick for handling this exact problem. So let's try a little experiment, you and me. I'm going to show you a quick video. All you have to do is count how many times the players in white pass the basketball. That's it. You ready? Pay close attention. Okay, so did you get the count? It doesn't really matter, to be honest. The real question is, did you see the gorilla? Yeah, the person in a full-on gorilla suit who walks right through the middle of the game. If you missed it, don't worry, most people do. This is a classic experiment that shows something called inattentional blindness, and what it proves is that our perception is totally task-driven. We don't just see everything. We look for specific things, and we're absolute pros at tuning out the rest. And that idea, the idea that seeing isn't passive but an active, goal-oriented thing, that is the absolute key to building a robot that can actually understand the world around it. This quote from the psychologist J.J. Gibson really says it all, and it's the core philosophy for the whole iRobot project. It's this beautiful feedback loop, right? We want to do something, say, grab a coffee cup. So that drives us to perceive, to look for the cup. And then the act of looking, of perceiving, is what gives us the information we need to act and grab it. See? Act to see to act. Okay, so great philosophy. Love it. But how do you actually turn that into code? I mean, how do you train a robot's eyeball to be this active searcher without just, hard coding a bunch of rules like look left, then look right? Well, the researchers came up with this really elegant solution called iGEM. And this is so smart. Instead of trying to build some super complex, probably going to be flawed 3D simulation of the room, they just stuck a 360-degree camera right where the robot's eye would be and recorded a person doing the task. That's it. Now they have perfect real-world video data. The AI can just train inside this video, looking around wherever it wants, practicing millions of times, and there's absolutely zero gap between the simulation and reality because the simulation is reality. So that data, that's the fuel. But the engine, the engine is this brilliant thing called the BCRL co-training loop. Now, I know this diagram looks a little intense, but trust me, at its core, it's just this elegant dance between two partners teaching each other, the eye and the arm. Let's break down how that dance works. All right, here's the choreography. Step 1, the eye. That's our reinforcement learning agent. It's the explorer. It learns by trial and error, just looking around the scene. Step 2, the arm. That's our behavior cloning agent. It's the student. It tries to do its job, but it can only use the information the eye gives it. Now, step 3 is the magic. The eye gets a reward based on how well the arm does. So if the arm successfully grabs the towel, the eye gets a little reward, like a gold star that basically says, hey, good job. That was a super helpful place to look. And they just run this cycle over and over and over, millions of times, until the explorer eye learns exactly how to be the perfect guide for the student arm. But a clever training loop is only one piece of the puzzle. The system also needed a really efficient way to actually process all that visual information. And to solve that, the researchers looked to nature, again, and what they landed on is something called foveated vision. It's exactly how your own eye works. You have that tiny little spot in the center of your vision that's super high resolution. That's the fovea, and it's for seeing all the fine details. But everything else, your peripheral vision, is much lower resolution. It's just for getting the general gist of the scene and noticing movement. So why is this so much better? Well, think about it. A standard uniform resolution camera is like trying to read a book by processing every single letter on every single page all at once. It's a colossal waste of computing power. Foveated vision is just smarter. It's like how you actually read. You focus your high-res attention on the words you're reading right now, while your low-res periphery keeps track of the page layout. It puts the brain power where it's needed most. And the architecture that pulls all this off is called the Foveal Robot Transformer, or FORT for short. Again, the diagram looks complicated, but the idea is actually pretty straightforward. It basically takes the main image from the eye, and then it creates a few smaller, blurrier copies of it. And the real trick is that FORT processes all of these different resolutions, from the sharp, detailed center to the blurry edges, all at the same time. What this does is give the robot this really rich, multi-layered understanding of what it's seeing. It can see the tiny threads on a screw and the toolbox it's sitting in, all in a single efficient snapshot. Okay, so let's recap. We have this clever training system where the eye and arm teach each other, and we have this super efficient, biologically inspired brain. So what happens when you put it all together? Well, this is where it gets really cool. You start to see these intelligent behaviors just emerge, things the robot was never explicitly told to do. Check this out, for instance. The eye completely learn on its own to switch targets. It'll stare at the towel while the arm is going to pick it up, but the instant it's grabbed, bam, its gaze flicks over to the bucket, already preparing for the next part of the job. And because of that foveated vision, it learns to lock onto a target and keep it dead center, this stable fixation. I mean, that's exactly what our eyes do. And the numbers absolutely back this up. Take a look at this task with the eraser. A robot with a camera on its wrist, it's perfect at picking up the eraser, 100% success rate. But if you then move the shelf where it's supposed to put the eraser, its success rate just plummets to 10%. Why? Simple. Its wrist can't see where the shelf went. But iRobot? It doesn't care. It just looks around, finds a new spot, and nails the task with 100% success. It can adapt because it can search. So look, this is way more than just a slightly better camera system. What we're seeing here is a clue to a much bigger, more fundamental shift in how we should even think about robot vision. What this all boils down to is a total change in perspective. It's about moving away from the idea of a robot as a passive observer that just gets fed a picture, and toward the idea of a robot as an active participant in its own environment, one that has to physically move and look and search to make sense of the world. And that leaves us with a really fascinating question to chew on. For decades, we've been trying to teach robots to see the world like a computer processes a file. But what happens? What incredible new possibilities open up when we stop doing that and start teaching them to see and interact with the world a little more like a living thing?